Welcome to the O-Level Chemistry lecture series. Today's topic is on acid bases, oxides, and a bit on ionic equations. So to begin this lesson, please make sure you have ready on hand the notes. The lesson will be delivered through the notes, through the PowerPoint, which will closely mirror the flow of the notes. Right, so these are some of the additional recommended practices: 10-year series, MRs, class tests, end of year papers, other schools' prelim papers, and external assessment books such as the 1001 chemistry book that you can obtain from Popular. So here is it. Today's topic: acid bases, a little bit on oxides, and a little bit on ionic equations. So let's move on to the topic proper. Quick definition of an acid is a substance which dissociates or ionizes to produce hydrogen ions when in water. Take note, there are 3 key points here: 1, 2, 3. So without writing any of these key points, you do not have the marks for the definition of an acid. So if I can represent this with a very simple generic equation, since I get hydrogen ions, H+, I can represent my acid as HX. In the presence of water, I get H+, and X-, AQ, AQ, presence of water, this is the acid. So in water, the acid dissociates to give me H+ ions, and this is the other constituent ion that makes up the acid. So H+ of the acid gives rise to most of the properties that an acid will exhibit. So here are some examples of common acids. You notice that there are 2 categories here. One is the mineral acids and one is the organic acids. Simply put, mineral acids are mainly man-made acids, and organic acids are natural acids. So you notice that most organic acids actually have the carbon element inside, and you notice that it is a COOH, COOH, COOH. They have the COOH here. What is the COOH? It is actually the carboxylic acid group, which we will cover more in the topic of organic chemistry. So mainly we are focusing on the mineral acids here and some of the more common organic acids such as ethanoic acid and methanoic acid. You notice all of them have H, 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 and H here, H here, H here, and H here, and H here. So all the H's here can dissociate when the acid is in water to give us H+ ions. But does all the H come out? Later on we'll take a closer look at this. So let's move on to some of the simple properties of dilute acids. You would probably have tasted a lemon your whole life. You will notice the lemon tastes sour. So the sour taste from the lemon actually comes from the acid, citric acid. To be precise, citric acid. So this is the acid which gives lemon the sour taste. So the more sour the lemon, actually the more concentrated is the citric acid content in the lemon. So acids have a pH of less than 7. So the pH scale is used to measure the acidity, the extent of dissociation of an acid. Later we'll see what is what I mean by the extent of dissociation. So for now, just take note that the pH scale runs from 1 to 14, and 7 being neutral. Acids are less than 7. So pH less than 7, acid. Right? So in order for us to quickly determine if something has a pH of less than 7, we can use litmus paper. There are 2 colors for litmus paper. There's blue litmus and there's red litmus. So acids turn blue litmus paper red. The other group of compounds, the bases, they turn red litmus paper blue. So we focus more on the acids one first, blue to red. Litmus paper, blue to red. If we use universal indicator, depending on the strength of the acid, it gives us either an orangey color or a red color. Red being for strong acid, orange being for a weaker acid. Universal indicator by itself, when it's neutral, it is green in color. So acids gives red color change, and bases gives a violet color change. We'll cover more on the bases later on in this topic. Now we come to some of the chemical reactions that acids undergo. So if the question were to ask you describe a chemical property of an acid, you will need to list down the chemical reaction. So for example, one of them is the acid-metal reaction. So acids react with metals to give us the salt and hydrogen gas. So the salt, if you observe, it's essentially H being replaced by the metal. So a salt is actually an ionic compound. It is formed by replacing one or more of the hydrogen ions of the acid here, with a metallic ion. So the metallic ion here in this case is Mg2 plus. Sometimes it can be the ammonium ion as well, NH4 plus. So this is the salt and this is the hydrogen gas. So acid metal reaction gives us salt and hydrogen gas. We can test for this hydrogen gas. If you recall, it will extinguish a lighted splint with a pop sound. Right? So if we stick a lighted splint into a test tube containing hydrogen gas, we will have the flame going out with a pop sound. Okay? Yep, so here is the diagram. Pop sound. This one is a special case. It's more of a special case for acid metal reaction. If we put lead into hydrochloric acid, this is the reaction which will take place. It's another acid metal reaction, but now this reaction actually does not proceed to completion. So the lead block does not completely react with all the acid. Why? Because PbCl2 formed here has the state symbol S. So this state symbol S actually indicates that the layer of lead 2 chloride surrounding the lead metal is insoluble. So if I have an insoluble layer around the lead, my HCl is here. There's no way for my HCl to come into contact with more lead for the reaction to take place. So after this layer of insoluble PbCl2 is formed around the lead, the reaction will stop. Okay, so the reaction will stop. So take note, do not react lead with HCl. Acids also react with carbonates and hydrogen carbonates to give us salt, water, and carbon dioxide. A common carbonate is calcium carbonate. This is limestone. So limestone is used to make the Taj Mahal. So you notice that the Taj Mahal has been eroded by acid rain. The acid in rain, which makes it acid rain, is dilute sulfuric acid. So now in this case I replace it with HCl. So acid and carbonate will react to give us salt, water, and carbon dioxide. Okay, so you give us salt, water, and carbon dioxide. For hydrogen carbonates, it's the same thing. So hydrogen carbonates with acid also gives us a salt, water, and carbon dioxide. So the carbon dioxide comes from the hydrogen carbonate or the carbonate portion. And to test for carbon dioxide, we can bubble it into lime water and it gives us a white precipitate. Do you know what is this white precipitate? Make a guess. Lime water is CaOH2, calcium hydroxide. So when we bubble in carbon dioxide, the precipitate we get is actually calcium carbonate. So this is the white precipitate that is formed. Acids also react with oxides and hydroxides to give us salt and water. So this is the oxide, this is the hydroxide. Hydroxide is, you can call it a hydrated oxide of sorts. So you notice that hydroxides are always in the aqueous state. Not always, it's most of the time you see them in the aqueous state. So the hydrated oxide, it reacts with acids to give us salt and water. Salt and water. So to recall, the salt is simply an acid with the H plus ion replaced by a metallic ion. Okay, with one or more H plus ions replaced by the metallic ion. Acids can also conduct electricity due to the presence of mobile charge carriers, which are ions. So, in for from the first definition of an acid is a substance which dissociates in water, dissociates in water to give you H plus ions. So notice that when HCl dissociates, you have H plus and Cl minus. So if I have a solution here with H plus and Cl minus inside, and I were to stick in two electrodes here, one with a positive terminal, one with a negative terminal, my Cl minus will migrate to the positive terminal, my H plus will migrate to the negative terminal, and this migration actually contributes to the flow of current. So in a sense, I'm saying that dilute acids can conduct electricity. Why? Because they have mobile charge carriers. How did these charge carriers come about? It came from the dissociation of the acid into the ions. So if I combine H2SO4 and HCl, I will be able to make a deduction that this is actually a better conductor than HCl. H2SO4 is a better conductor than HCl. Why? Because for every unit of H2SO4, I have 2 plus 1 unit of ions versus 1 plus 1 unit of ions. So I have 2 units of ions here, I have 3 units of ions here. So because I have more mobile charge carriers, I can make a deduction that H2SO4 is a better conductor of electricity. Okay, now we move on to this very important area on water being required for the properties of an acid. So if you recall the definition from earlier, the acid must dissociate to give us H plus ions in water. So H plus ions only exist in the presence of water. Without water, you have no H plus ions. No H plus ions, you cannot have an acid. And because the acidic properties of an acid comes about from the presence of the H plus ions, so if I have HCl reacting by itself, there will be no reaction. It's only when HCl dissociates into H plus and Cl minus and the H plus undergoing the reaction here, then I can observe the acidic properties of HCl. So without water, no H plus, no acidic properties. Right? So if you have seen this before, this is an example of effervescence tablet. The tablet by itself remains relatively inert, but once you pop it into a glass of water, you notice fizzing happening. So this fizzing is actually a reaction between an acid and a carbonate. What acid is being reacted? It is actually citric acid. So in the tablet, there is citric acid in the crystalline form. So in the crystalline form, there is no water present. It is just a citric acid molecule, no water. But when you put it into the water, into this cup of water, water is present. Citric acid dissociates to give you H plus ions, and these H plus ions react with the carbonate in the tablet, giving rise to the fizzing. So this fizzing actually helps to break the tablet into smaller pieces and dissolve the tablet well in this cup before you drink it, of course. So, to recap, an acid does not behave as an acid unless water is present. We need to have AQ for the H plus ions to form through dissociation of the acid molecule. No H plus, no acid. So how do we confirm this? It's actually very simple. So if you recall the earlier properties of the acid, these are the tests based on the properties of the acid. If I dissolve HCl in water, I will have the H plus ions. If I dissolve HCl in methyl benzene, this is an organic solvent, means no water, so I have no H plus ions. The HCl in water will be able to turn my blue litmus paper red. This one remains blue. Why? Because there's no H plus. It can conduct electricity. Why? Because my HCl is now dissociated into H plus and Cl minus. Over here it remains as HCl molecules, no dissociation, no mobile charge carriers, so cannot conduct electricity. I add magnesium ribbon. I have my HCl reacting with Mg to give me my salt plus hydrogen gas. So I get effervescence and I have hydrogen gas. No visible reaction because there's no H plus again. This is my base. Adding a base can react with HCl, so this is acid-base reaction. I can get a blue solution of Cu2 plus ions. Over here, no visible reaction as well. Adding carbonate, I have an acid-carbonate reaction, so this is an acid-carbonate reaction. And I have my CaCl2 plus H2O plus CO2. So I observe effervescence, and I observe the evolution of carbon dioxide. Why? Because H plus is present. No H plus, no visible reaction. Why? So why do I keep harping on the point that there's no H plus? There's no water, there wouldn't be any H plus for any reaction to take place. This is because acids, in the absence of water, is actually a small covalent molecule. So let's recall how do we draw HCl. If I were to draw the dot and cross diagram for HCl, it will look something like this. Okay, so HCl, single bond. HNO3 is a bit more complicated. It's something like this. And H2SO4 is a bit more complicated. It is something like this. So notice that in all these three molecules here, they are all covalent molecules, and they all have covalent bonds. Covalent bonds, covalent bonds. And the covalent bonds actually bind the H to the oxygen atom here. Okay, or it binds it to the chlorine atom here. So the H cannot be released. So it is just a simple molecule by itself. But when you add in water, the water molecule can actually remove the H from the acid molecule. So it gives us the H plus ion, which then can allow us to have all the observations for the different reactions of an acid. So actually, to be more precise, if you observe this equation here, the H plus ion is in fact something like this. It is formed between the reaction of water with the acid. It gives us H3O plus Cl minus. So this is called the hydrozonium ion. But for O level, we simplify this into the H plus ion. So H plus is sufficient for O levels. H plus, and H plus. So this process by which the acid breaks out the H plus is known as ionization or dissociation. So when I have an organic solvent, nothing happens. I simply dissolve the HCl and it forms a liquid HCl. So how do the organic molecules dissolve HCl? Is by means of van der Waals forces, if you recall. So the weak van der Waals forces, they bind the HCl molecules and then they disperse them in solution, allows the HCl gas to dissolve. But when it dissolves, there's no dissociation happening. This doesn't take place. This doesn't take place. So there's no H plus. So no H plus, no acidic properties. So now let's move on to checkpoint 1. Pause the video now to attempt this checkpoint. Continue with the video once you are done. So what are the 3 properties of an acid? Earlier we recalled we have a couple of them. Sour taste, pH less than 7. We have the reaction with metals to give us salt and hydrogen gas. We have the acid carbonate reaction to give you salt, water, and carbon dioxide. Acid metal oxide reaction give you salt and water. The ability to conduct electricity. So here is it. You have the main property, sour, less than 7. It reacts with metal to give you salt and hydrogen gas. Carbonates or hydrogen carbonates give you salt, water, and carbon dioxide. With oxides and hydroxides give you salt and water. And it can conduct electricity due to the presence of mobile ions. So what equations can we write to show the reaction of dilute hydrochloric acid with carbonates and lithium? So this is a acid carbonate reaction. What do we get? We have 3 things. We have the salt, we have water, and we have carbon dioxide. With acid metal, we have salt and hydrogen gas. So first one, Na2CO3 plus HCl, NaCl plus H2O plus CO2. How do we know what is the salt? It is actually a very simple trick. Just take the first one and the second one and we do a swap. Because if you recall, the salt is an acid. with the H plus replaced by a metal ion. So there's only one acid here, which is HCl, and there is only one other metal ion here, which is Na. So you can only replace the H of HCl with Na from Na2CO3. That's why we have NaCl, sodium chloride here. The rest of it is the generic equation, water and carbon dioxide. So lithium with water, lithium with acid, what do we get? Same things as usual. The salt, LiCl, the H of HCl is replaced with the metal. So the only metal here is Li, so we put in Li, LiCl, and we have H2. This is from the generic equation. So acid plus metal gives us salt and hydrogen gas. So quick recap, how do we test for this? It extinguishes a lighted splint with pop sound. Lighted splint and extinguish with pop sound. What about CO2? It forms a white precipitate in, yes, lime water, correct. And recall what's lime water? Lime water is CaOH2, calcium hydroxide. Now let's write three equations to show the reaction between dilute sulfuric acid with potassium carbonate, magnesium and sodium oxide. So the first one is an acid carbonate reaction. We will have salt, water and carbon dioxide. Acid metal, we have salt and hydrogen gas, and acid sodium oxide, we have salt plus water. So now we have this, we will be able to write this out. K2CO3 plus H2SO4 gives us salt, water and carbon dioxide. Acid metal, salt and hydrogen gas, and acid oxide gives us salt and water. Take note, SO4 has a charge of SO4 2 minus charge, H plus, that's why we have two H's here. K is in group 1. Group 1 means that it will lose a single valence electron to form K plus. So to balance 2 minus and plus, we need 2 of the K's. Mg is from group 2, so it loses 2 electrons to give Mg2 plus. So we just need 1 Mg2 plus to balance the SO4 2 minus over here. Na, as usual, is the same. It is from group 1, so we get Na plus E minus. So in order for sodium sulfate to be charged neutral, we need 2 Na plus to balance away the 2 minus from the sulfate ion. So now let's go on to the basicity of an acid. There are three main basicities here, which we will cover for today. One is the monobasic acid. If you see, it's quite obvious. Mono means 1. So each acid molecule only gives 1 H plus if it is dissociated. Dibasic acid or diprotic acid. Protic is basically the word for proton, because H plus essentially is only one single proton. Because hydrogen is 1 proton and 1 electron. When it loses the 1 electron, it's left with 1 proton and it gives the H plus. So this is a monoprotic acid or monobasic acid. This is a dibasic acid or diprotic acid. So you notice each molecule, when fully dissociated, can give us 2 H plus. So this is supposed to be H. This is out. Not here. This is supposed to be over here. Okay, so tribasic acids or triprotic acids, H3PO4, H3PO3, when they dissociate, they will give us 3 H plus ions each. So this refers to the maximum number. Notice this is the maximum number of H plus ions that can be replaced by a metal. So it doesn't need to replace all 3 at the same time, but this is the maximum number that can be replaced by a metal during a acid metal or acid salt or acid oxide reaction, or one of the other reactions which covered earlier in this topic. Okay, so for example, if I were to write a simple one, H2SO4 plus, let's say, magnesium, we'll write MgSO4 plus H2 but it can also replace just one H. So for example, if we have H2SO4 with sodium, we could get NaHSO4 plus H2. Okay, so this is possible as well. Balance the equation with a half here. So this is the first step of the reaction. The second step will be the HSO4 minus. Na is plus, so this is HSO4 minus. It can be the HSO4 minus reacting with another Na to give us Na2SO4. So it's a two-step reaction, which we always write as a single step, such as this. So let's quickly do checkpoint 2. We have 3 acids here, one monobasic, one dibasic, one tribasic. So write down the dissociation equations to represent these 3 types of acids. So monobasic one, you could think of HCl, we have 1H plus, dibasic one, probably H2SO4, and we have 2H plus, 2, 2, 1, 1, and the tribasic one we have phosphoric acid, H3PO4, this is phosphoric acid, and when it dissociates fully, we have 3H plus ions. Now, let's move on to an area which is often confused by many people, the strength of an acid versus the concentration of an acid. So, take note, these two terms are not the same. The strength refers to how much it is dissociated. So, for example, HCl I would say is a strong acid because it is fully dissociated. So, if I have 1 mole of HCl, at the end of the day, I will have 1 mole of H plus and 1 mole of Cl minus. So let's ignore this part first because this is the more important part. If I have 1 mole of HCl, I would get 1 mole of H plus in water. Because why? HCl is fully dissociated. The HCl bond breaks to give me H plus and Cl minus. So weak acid is one which is partially dissociated. It means it is not fully dissociated or not fully ionized in water. For example, I have ethanoic acid over here. You notice that the arrow here is a reversible arrow. This is a reversible arrow. So it shows that the reaction, this reaction step is not complete. And only some of the ethanoic acid molecules actually dissociate to give me H plus and the ethanoate anion. So because it is not a full 100% dissociation, if I have 1 mole of this, I will have much less than 1 mole of H plus. Much less. So this means that this acid is a weak acid versus a strong acid which is fully dissociated. So this is a very simple pictorial representation. I have all my HCl fully dissociated, but I only have 1 ethanoic acid molecule dissociated. So this is a weak acid, partial dissociation, and this is a complete dissociation for a strong acid. So as a result of this, what happens? It means that strong acids react more vigorously than weak acids in the same reaction. So if I have magnesium ribbon here, let's say this is magnesium ribbon. So Mg plus HCl, I have a lot more H plus compared to ethanoic acid. So because I have a lot more H plus, the reaction proceeds more vigorously, and I get more H2 gas being evolved. And as a result, when I do my Lighted spleen test, there's a much louder pop sound. Pop versus pop. This is a loud pop versus a small tweeny pop. So now let's move on to concentration of an acid. So versus strength, what is the difference? Concentration is simply the amount of acid per unit volume. Con is the amount of acid per unit volume. So I can have a concentrated weak acid and I can have a dilute strong acid. So for example, if I have HCl, this is a strong acid. If let's say I only have 0.1 mole in 1 dm cube of solution, my concentration would be 0.1 moles per dm cube. And if I have my ethanoic acid here over here, and I have say 1 mole of ethanoic acid, and I have the same volume of water, I get 1 mole per dm cube of ethanoic acid. So this is a higher concentration of weak acid, but I do not change the strength of the acid. So this is the strength remains unchanged. The strength is only dependent on the acid itself. The strength is dependent on the acid itself. The concentration is dependent on the initial amount or mass you add into the water. So take note, make sure you are very clear on this. The strength is only dependent on the acid itself. You cannot change the strength of an acid by using more or less of the acid. It is dependent on the acid. HCl is forever a strong acid, ethanoic acid is forever a weak acid, but I can have a concentrated solution of a weak acid and a dilute solution of a strong acid. So this is a quick table which summarizes this. This is 10 moles per dm cube. Let's say I have a con solution of a strong acid. This is a dilute solution of a strong acid still. This is a con solution of a weak acid, and this is a dilute solution of a weak acid. The con does not affect the strength of the acid, right? The con does not affect the strength of the acid. Very important point, take note of this. So over here you'll see some examples of acids in everyday life. The first one is the effervescence tablet, which we have the citric acid. So this is actually a weak acid. You have dilute sulfuric acid in your car batteries. This is a very strong acid. Over here we have a bomb. So the bomb, there can be acids in the bomb. Nitric acid is one such acid in bombs. So nitric acid is a strong acid. And soaps, some soaps contain acids. Why? Because your skin is slightly acidic, about pH 5.5 around there. So to balance the pH of your skin, the soap sometimes contains a little bit of weak acid, such that when you wash your skin, the soap is at the same pH as the skin and it wouldn't damage or dry the skin. So these are useful uses of acids. But are there not useful uses of acids, or harm which acids can cause? Yes, of course. So acids in the environment. For example, take a look at this. This is a power station which burns coal. Coal contains loads of sulfur, and when you have loads of sulfur burning in oxygen, you get sulfur dioxide, and sulfur dioxide can dissolve in water in the rain to give us acid rain. Similarly for here, this is the exhaust pipe of a car. You have loads of stuff coming out. For example, you have carbon dioxide. Carbon dioxide, you have nitrogen dioxide. So these two oxides can dissolve in water to give us acids as well. So the first one gives us carbonic acid, and the second one gives us nitrous acid or nitric acid. So all these are acids which are bad for the environment. So we will touch a little bit more on acid rain. The sulfur dioxide which comes from burning of coal can dissolve in water first to give us sulfuric acid. Take note, this is SO3. SO3, not SO4. So how do you know it's 3? Very easy. 1, 2, 3. There are 2 here and there is 1 here. So 3, sulfuric acid. So in the presence of oxygen in the air, your sulfur dioxide here dissolves in oxygen. Can be further oxidized to give us SO3. So this is sulfur trioxide. And sulfur trioxide can dissolve in water to give us dilute sulfuric acid. This H2SO3 formed here can also be further oxidized by oxygen in air to give us sulfuric acid. So all this contributes to acid rain, and this is no good. Why? Because it destroys your structures, it damages crops, it kills fishes. Basically, it's no good, no. The Taj Mahal has been partially dissolved by acid rain. Large tracts of land have been made barren and unsuitable for farming because of acid rain. lakes have been polluted and the fish have been killed because of changes to pH, because of acid rain. So how do we reduce acid rain? We must reduce the sulfur dioxide. How do we reduce sulfur dioxide? We must stop burning of coal. How do we stop burning of coal? We can switch to alternative fuels, or we use less electricity. So do your part and save the environment. Nitrogen dioxide formed through industrial processes can also dissolve in water to form a mixture of nitrous oxide and nitric acid. So NO2 is mainly formed in car engines. It's mainly formed in car engines because the very high temperature in the car engines can allow for the very strong N triple bond to break and react with oxygen to give you NO2. So NO2 is released into the environment. It dissolves in water, gives us nitrous acid and nitric acid. So these two acids also contribute to acid rain. And even in the absence of these pollutant gases, rainwater will be slightly acidic. Why? Because air contains carbon dioxide. 0.03% of air is carbon dioxide. And carbon dioxide is soluble in water. So even without any pollutants, CO2 can dissolve in water to give you carbonic acid. This is a weak acid. So rainwater is slightly acidic. Okay, so if you have the chance to get some litmus paper, you could probably get it from the lab, or you can buy them from the Guardian or Watson's pharmacy. You can collect some rainwater in a cup next time it rains and dip in the litmus paper to see the color change from blue to red, indicating that rainwater is actually acidic. Yep, so this are some pictures showing the detrimental effects of rainwater. No good. Kill fishes, destroy plants, destroy statues. Basically, no good. No good. So we have come to the end of the acids portion for this topic. We will now move on to the base portion of this topic. So acids, the bases are can be thought of as the opposite, inverted commas, of acids. So the properties which acids exhibit are not the same as that exhibited by the bases. They are opposite, but they undergo very similar reactions as well to the acids. So let's take a look at what are the reactions that bases undergo. So before we begin, let's again define bases. They are the oxides or hydroxides of metals. So if we take a look here, this is the metal oxide, this is magnesium oxide, this is copper 2 oxide, zinc oxide, magnesium hydroxide, aluminum hydroxide. Notice that all this here are metals. So metal oxides are bases. Right? Metal oxides are bases. And if the base is soluble in water, we call it an alkali. So it dissolves in water to give us hydroxide ions. We call it a alkali. So a very simple example would be NaOH. So Na2O, this is sodium oxide. This is a metal oxide. So this is a metal oxide. It means that it is a base. And because Na2O can dissolve in water to give us NaOH, it can dissolve in water to give us NaOH. Let's balance this equation. We shall put a 2 here. 2 O's, 2 H's, 2 Na's, balanced. So because it can dissolve in water to give us NaOH, we call this an alkali. Right? So metal oxides are bases. If the base is soluble in water, we call it an alkali. Take note, do not confuse these two terms. And from the definition above, NaOH can dissociate to give you Na plus and OH minus ions. Right, so an alkali is a soluble base which dissociates in water to give us the hydroxide ions over here. So here are some of the common bases and common alkalis which you encounter. The one which I already mentioned earlier, here, Na2O. So potassium oxide, calcium oxide, or quicklime. This is used to lime fields, farming fields. When you notice this releases OH minus, so if there's a mild acid rain attack on a farm and the soil is too acidic for plants to grow, the farmers can actually use quicklime, scatter over the field. The OH minus produced will neutralize the H plus and adjust the pH back to normal. NH3 ammonia, aqueous ammonia, sodium hydroxide, NaOH, these are common alkalis we see in the lab. And this last one, CaOH2, is also known as lime water. Alright. Okay, so now moving on to the properties of alkalis. They have a bitter taste and they feel slippery and soapy. Your soap, in fact, most of the soap at home, most of the soap contains alkalis. So if you don't believe, go back. When you are bathing yourself today, lick yourself when you have applied, after you have applied soap. You'll notice that it is extremely bitter. Right, it's extremely bitter. So why do alkalis feel slippery or soapy? This is because the alkalis by themselves, they are not slippery or soapy, definitely, but the alkalis can dissolve the very, very thin layer of oil on your skin surface. So when it dissolves this very thin layer of oil and fat on the skin surface, you feel that there's less friction when you rub your fingers together. So as a result, you notice this slippery or soapy feeling from touching alkali. So it is not the alkali that is slippery, it is actually the fats or the oils on your hands or your fingers that has been dissolved and reduces the friction when you rub your fingers together. So acids have a pH of less than 7, alkalis the opposite, they have a pH greater than 7. The max pH is 14, and acids turn red litmus paper blue, alkalis turn acids turn blue litmus paper red. So alkalis do the opposite, they turn red litmus paper blue. Okay, so red to blue are alkalis. A good way to remember this is actually Al, red to blue. So I use this mnemonic to remember. Ali reads books. So Ali, Al stands for alkalis, reads stands for red, B stands for blue. So alkalis turn red litmus paper blue. Universal indicator, it turns it purple or violet depending on the strength of the alkali. Recall what's the color for acids in the universal indicator? It is red or orange. Similar to acids, alkalis can also conduct an electric current. Why? Because they can dissociate in water to give you the mobile ions. So when you have mobile ions, you can migrate to the electrodes. So if you have a plus and minus here, the negative ions can migrate here, positive ions can migrate here, and this migration constitutes the flow of electric current. So alkalis can conduct electricity. This last definition here is actually quite important. The alkalis can react with acids to form salt and water only, and this particular reaction is known as neutralisation. So if I have KOH and HCl, I get salt and water. We call this reaction neutralisation. Take note, you cannot apply neutralisation if it's a acid carbonate reaction. Only if it's an acid base reaction giving us salt and water can then we use the term neutralisation. Ammonia and HCl, same thing, it gives us a salt. In this case, there's no water present, but we can still call this a neutralisation reaction. Why? Because the ammonia reaction is actually 2 steps. NH3 actually first reacts with H2O to give us NH4 plus OH minus. And this OH minus then reacts with the acid component to give us H2O and Cl minus. So when I combine these two equations together, what do I get? I have NH3 plus H2O plus HCl plus OH minus, giving us NH4 plus OH minus plus H2O plus Cl minus. So when I cancel out the water on this side and this side, and I cancel out the OH minus on this side and this side, what I have left is simply NH3 plus HCl, giving me NH4 plus Cl minus over here. So NH3 plus HCl giving us NH4Cl. So the water and the OH minus cancels out on both sides of the equation. Sometimes you may have seen this equation before for aqueous ammonia. So aqueous ammonia, some books or maybe some form of media, they represent aqueous ammonia with this NH4OH, and they call this aqueous ammonia. This is actually absolutely wrong. Okay, this is totally wrong, because aqueous ammonia is not NH4OH. It is simply NH3AQ. And NH3AQ can react with water to give us NH4 plus OH minus. So this is the OH minus which gives rise to the basic properties of ammonia here. For example, in the equation I wrote earlier, NH4 OH minus plus the HCl gives us H2O plus Cl minus. So this is the OH minus from ammonia. It is not NH4OH. This is wrong. Please do not write this. Aqueous ammonia is NH3 bracket AQ. Okay, so the reaction between NH3AQ and HCl AQ gives us NH4Cl in this way. It is not NH4OH. If I were to summarize out the key components of the neutralization reaction, I actually only have left with these ions, H plus, OH minus, giving us water. How in the world did I get this equation out, or what we call the Ionic equation? Later on at the back of this topic, we will go into more depth on the derivation of the Ionic equation from a common chemical equation. So for now, we will just take note that neutralization reaction is simply H plus OH minus giving us water. So the H plus comes from the acid, OH minus comes from the base, and they react to give us water. So this is the neutralization reaction. Alkalis can also react with ammonium compounds to give us salt water and ammonia gas on heating. Without heating, this one actually doesn't take place, or takes place extremely slowly. So when you heat the alkali with ammonium compounds, we have NH3 evolve. So this is the equation. Where did the NH3 come from? It's because the OH minus here reacts with the NH4 plus here. This is the ammonium ion. Take note, NH4 plus is ammonium, NH3 is ammonia. Most commonly confused, they are not the same. So when these two react in the presence of heat, we have NH3 plus water. So this is a gas, and this is lost to the surroundings, and you smell a pungent odor from the ammonia gas. Okay, and because NH3 gas, when dissolved in water, gives us OH minus, we can test for this gas with red litmus paper, which is moist. Why moist? Because we need to have water present to allow the OH minus ions to exist. This next property of alkalis is widely applied in QA. So we add sodium hydroxide, or we add NH3 or equals ammonia to precipitate out some metal ions, and based on the color of the metal ions, we can deduce what is the metal ion present. So for example, if I add sodium hydroxide into copper 2 sulfate here, I will get a blue color precipitate. And this blue color precipitate is actually copper 2 hydroxide. And when I see this blue color, I can immediately deduce that in the original solution there is Cu2 plus present. Okay, there's Cu2 plus present. Likewise, when I add ammonia into an aqueous solution containing FeCl3, the ion present is Fe3 plus, I will get a reddish brown precipitate of iron 3 hydroxide. So by seeing this, I know that there's Fe3 plus present. So this reaction is known as a precipitation reaction. Why? Because I get a precipitate form during the reaction. So the precipitate is simply the insoluble salt. It's simply the insoluble salt. Okay. Alright, so now let's move on to checkpoint 3. You can pause the video now to attempt the checkpoint. Continue the video once you are done. Now let's move on to checkpoint 3. Right, simple chemical equations with state symbols. Take note with state symbols to show the reaction of a base with an acid and a base with a ammonium chloride with heating. Take note this is solid, so to write AQ. Dilute HCl will be AQ. So for the first one, we have NaOH with HCl giving us salt and water, and state symbols in. This is AQ, this is AQ, this is AQ, and for water it is liquid. For the next one, we have sodium hydroxide, AQ again. This is solid, this is the AQ. Ammonia is a gas, and water is in the liquid state. So we have the base and ammonium compound giving us salt and ammonia and water. So how do we know there's ammonia being produced? Because we have a ammonium compound here, and the N must balance on both sides. The next three equations are for simple precipitation reaction with state symbols, so we need to know which of the salts formed are soluble or are insoluble in water. So first one, iron 2 nitrate plus aqueous sodium hydroxide. Iron 2 nitrate, it will give us a solid. This is a solid. This is our dirty green precipitate. So we need to write the state symbols in. This is AQ, this is AQ, this is solid, and this is AQ. All nitrates are soluble in water. All compounds of nitrates are soluble in water. All compounds containing Na is soluble in water. All compounds containing nitrates are soluble in water. Next one is zinc 2 chloride with aqueous sodium hydroxide. So we get ZnCl2 plus NaOH giving us ZnOH2 and NaCl. Zinc hydroxide is also insoluble in water. This is a white precipitate. This is soluble in water because this is common salt. This is the base. This is the alkali. So yes, and this is the zinc chloride. So yes, this is aqueous zinc 2 chloride. The last one is aqueous iron 3 sulfate with aqueous potassium hydroxide, giving us iron 3 hydroxide. This is a reddish brown precipitate. This is the reddish brown precipitate. So being a precipitate, this is a solid because it is insoluble in water. All potassium compounds are soluble in water. This is the base, and this is the aqueous sulfate. So it's AQ, AQ, solid, and AQ. To recap on which compounds are soluble or which compounds are not soluble, look through the solubility table. Alright, look through the solubility table in the topic of metals or the preparation of salts. Okay, so similar to acids where there's the monobasic, dibasic, and tribasic acids, we also have bases which are monobasic, dibasic, and tribasic. So NaOH, for example, contains one OH minus which could possibly dissociate out. Dibasic acids, calcium hydroxide 2, aluminum hydroxide 3. So basicity of a base, it simply refers to the number of moles of hydrogen ions that is required to react with 1 mole of the base. So NaOH, you only need 1 mole of H plus to give us the water. But for AlOH, 3. For complete reaction, we need 3 H plus ions to give us 3 moles of water. Okay, simple. So let's do a quick checkpoint 4 on what are the simple equations to show the dissociation of a dibasic base here, calcium hydroxide. So it's just this, gives us Ca2 plus and 2OH minus. So state symbols in AQ, AQ, and AQ. We now move on to the strength of an alkali. So similar to the strength of an acid, the strength of an acid, it refers to how much dissociated is the acid molecule. So this is the same for alkalis. If I have a strong alkali, it undergoes complete dissociation, and during this dissociation, it gives me the hydroxide ions. So NaOH and KOH, they are strong alkalis because they are fully dissociated in water. The weak alkali, for example, ammonia. This is a reversible arrow. So for every 1 mole of NH3, I do not get 1 mole equivalent of OH minus. I get much less than 1 mole. So as a result, I can say that the ammonia, aqueous ammonia, is actually a weak alkali because it does not form 1:1 of OH minus in water. So here are some common examples which contains alkalis. Antacid here, this is the medicine which you take when you have gastric pain. Gastric pain sometimes is caused by excess acid in your stomach, and your stomach contains hydrochloric acid. So if you have too much HCl, you take some antacid to remove the H plus from HCl. So no H plus, no acidic properties, then your pain will go away. Fertilizers sometimes contains bases. Why? Maybe they need to neutralize the extra acidity in the soil. Your soaps contain bases because bases are very good to be used in dissolving fats, dissolving dirt. Cement, or this is cement. Cement contains a base as well. A base is mixed in to make cement. Then there are actually many other sources of hydroxides that you commonly encounter every day. Batteries, for example, your energizer cells, your Duracell cells. Inside there's a electrolyte which actually contains a base. It's likely to be potassium hydroxide. Okay, so let's do a very quick and simple checkpoint 5 to recap your acids and your bases before we move on into the next part of the topic, which is indicators and the pH scale. So pause the video now to attempt this checkpoint. Continue the video once you are done. Alright, so for checkpoint 5, which one of the beakers below represent a corn solution of a weak acid? Corn solution means that you must have a lot of the acid per unit volume. So you have corn equals to number of moles over volume. Number of moles over volume. So you must have a lot of moles in a unit volume. A weak acid is partially dissociated in water to give H plus ions. So if we take a look around here, we have a clustering of ions in B and D, but we observe that in B, most of it exists as H plus and X minus, versus D, most of it exists as HX. So we can conclude that D is the answer because D has the most number of particles per unit volume, and most of it is not dissociated. There is only a couple of ions, if you notice here, X minus and H plus. So in which of the following reactions is dilute nitric acid not behaving as an acid? So let's do a quick recap. Acid reactions. We have acid base giving us salt and water. We have acid metals giving us salt and hydrogen gas. We have acid carbonates giving us salt and water and carbon dioxide, and we have the acid and oxides giving us salt and water. So if we scan through these four equations here, I have an acid metal reaction giving me salt and hydrogen gas, so this is correct, it's behaving like an acid. I have an acid and a hydroxide here, hydroxide oxides giving me salt and water, so this is correct. I have an acid with a carbonate giving me salt, water and carbon dioxide, so this is correct. And for the last one, I have an acid and a metal, which by right should give me salt and hydrogen gas, but I have a salt, I have NO, and I have water, I have no hydrogen gas. So in this case, dilute nitric acid is not behaving as an acid, so the answer is option D. So in this reaction, what is actually happening? Dilute nitric acid is in fact a very powerful oxidizing agent. Okay, so being a very powerful oxidizing agent, it doesn't undergo a typical acid metal reaction. It oxidizes the copper to something else, and during the reaction I have nitrogen oxide being released as well. So this will be covered more in fact in the A levels. So part 3, which of the following reactions is the metal oxide not behaving as a base? So if a metal oxide were to behave like a base, it will undergo an oxide-acid reaction to give me salt and water. The metal oxide can also react with ammonium compounds to give me salt, water, and ammonia gas. So if we look through these four equations here, let's start from the bottom. I have a metal oxide and an ammonium compound giving me salt, water, and ammonia gas, so this is correct. I have a metal oxide with ammonium compound giving me salt, water, and ammonia gas, so this is correct. I have an acid here and a metal oxide giving me salt and water, so this is also correct. And for the first one, I have an acid with a metal oxide. By right, it should give me salt and water. I have salt, and I have water, and I have chlorine gas here. Aha! So in this case, a metal oxide is not behaving as a base. So the answer is A. Now, let's move on to the part of this topic on indicators and pH scale. So how do we know whether a substance is an acid or an alkali? We can make use of the litmus paper, correct? So litmus paper, the red litmus paper will turn blue if there is in the presence of an alkali. The blue litmus paper will turn red if there is an acid. We can also make use of some substances which we call indicators, which will give us a visual indication of whether the substance is an alkali or an acid. So for example, the first one is phenolphthalein. It turns pink in alkalis. Methyl orange is the one which we most commonly use in the lab. This one is the most common in the lab. It is red in acids, it is yellow in alkalis. Litmus, as we mentioned earlier, is red in acid and it is blue in alkalis. So what does the indicator actually measure? It measures the pH of an acid. So what is the pH of the acid or base? So the pH is actually a measure of the acidity of an acid or the basicity of an alkali, So this is only measured when the substance is dissolved in water. So to go on to a little bit more depth on what is pH, pH is actually a negative log of the concentration of H plus in the solution. So if I have a higher concentration of H plus, I will have a lower pH. So that's why if I have a strong acid which is fully dissociated, I will have a low pH. If I have a weak acid which is not fully dissociated, my con of H plus will be much lower. So much lower con H plus, it means that when I negative log a smaller number, I will have a large pH. Try to sub in certain values. Maybe try to sub in con of 1 versus a con of 0.01, and you will be able to see for yourself why a strong acid which is fully dissociated will have a much lower pH than a weak acid that is not fully dissociated, okay, in the presence of water. So for bases, it is simply 14 minus the pH, and we get a value for the bases. So for acids, they have more H plus and OH minus. For alkalis, they have more OH minus than H plus, and when it is neutral, they cancel out. So take particular note that in an acid there is still OH minus. It is just that the con of H plus outweighs that of the OH minus. Similarly in alkalis, there is still H plus, but the con of OH minus outweighs that of the H plus. In neutral, it is the same, equal. So this is a table which shows the color changes of some of the indicators. So let's take a look for, say, screen metal orange. In acids, it is red. In alkalines, it is yellow. But take note, the color changes only at 3.7. So if it changes yellow, it may not truly be a acid. It could be pH 4. Because at pH 4, it will be yellow already. Correct? So how do we ensure that when we add metal orange, we know that that solution is indeed an alkali? We can always use a combination of indicators. So for example, we can use, if we test a solution with metal orange and it gives us yellow, we can deduce that the pH will be above 3.7, but we cannot deduce that the substance is an alkali. What we can do is now to use, say, litmus, and we get a blue solution, and then we can conclude it is above pH 7. Okay? But if when I use litmus, I get a red color solution. Okay, so this solution X in metal orange, it is yellow. In litmus, it is red. It tells us that because it is yellow, it must be pH more than 3.7. Correct? The pH must be more than 3.7. Okay, the pH must be more than 3.7, must be above 3.7. And because it is red in litmus, the pH must be less than 7. Correct? So if this solution X gives me a red color litmus and a yellow color metal orange, I will know that the pH for this solution X will be between 3.7 and 7. Correct? Yep. So to narrow this down further, let's say I use screen metal orange and the solution still remains red. It tells me that the pH is between 3.7 and 4. But you notice, right, when I use a mixture of indicators here to tell me the pH of the solution, it's actually not a very precise value which I obtain. It's always a range between whatever and between whatever. So how do we actually get a more accurate indication of the pH of a solution? There are two ways. The first way is still not very accurate, which is to use universal indicator. It gives us a range of colors from red to purple. Universal indicator is actually a mixture of different indicators. It's a mixture of indicators. So based on what is the pH of the solution, it gives us a color. Okay, but this is also not very accurate, because if it is blue, it can be 10, it can be 10.5, it can be 11, it can be 11.1. So it is not very accurate. The most accurate indication actually is given to us by something which we call the pH meter. So a pH meter is an electronic device which measures the concentration of H plus ions based on the measurement of the conductivity of the solution. So we can see what is the conductivity of the solution, and we will be able to determine what is the pH of the solution. So let's say this solution here, the pH meter here shows 7.00. So we can say that this solution is neutral. Okay. Alright, so this is a example of a range of pHs which we can find in nature. In foods, for example, most pickled foods are acidic because the pickling involves the use of ethanoic acid. And ethanoic acid, when it is mixed with water, a low count of ethanoic acid in water is actually called vinegar. So all these are vinegary foods. They are pickled, and the acid helps prevent the growth of harmful bacteria and mold. So these foods can be stored for a much longer period of time. In our human body, the pH changes from our mouth all the way down into our stomach. Our stomach is acidic. Our intestines are, small intestines is actually a bit alkali. So you notice the pH changes as the food moves through our body. Okay, so why are the different parts of our stomach having different pHs? It is because the enzymes in these two areas, in these two areas have optimum pH values have different optimum pH values. So for the enzymes in the stomach, they work better when it is acidic. For the enzymes in the small intestines, they work better when it is alkali. You can read up more about this in the human digestive system or the alimentary canal topic. Alimentary canal topic in biology. Plant growth is also affected by pH values. So in this table here, which is shown here, you notice there are 4 pH values for 4 different types of soil. So depending on what plant you are growing, you will need to calibrate the pH of the soil to allow the plant to grow best. So let's say, for example, maybe tomatoes. Let's say tomatoes grow well in pH 6 soil, and your soil is a pH 8. So you need to bring down the pH to 6. So what do? You add in some acids. Okay, so but at the same time, if your soil is too acidic and your plant requires a more basic condition to grow, you can remove the acid in the soil by adding in bases such as calcium oxide or alkalis such as calcium hydroxide. So this is a metal oxide. A metal oxide is a base. If it is soluble in water, it is an alkali. So the presence of these two, they can help remove the H plus ions in solution. They can remove the H plus ions from the soil, and it will raise the pH of the soil. So if our soil is too alkaline, we can add in ammonium sulfate. Ammonium sulfate is acidic. Where is the H plus from? Ammonium sulfate, when it is dissolved in water in the soil, it dissociates to give us NH4 plus and SO4 2 minus. And the NH4 plus here can partially dissociate to give us NH3 and H plus. So this is the source of H plus. So this H plus can react with the excess OH minus in the soil, and it will lower the pH to a suitable pH. This is an example of shampoo and conditioner. So why is a shampoo and conditioner here? I will not review too much here. Why not you ask your chemistry teacher, or you go to the pharmacy to buy some litmus paper and you test the pH values of test the pH of the shampoo and the conditioner. You will find that one is acidic and one is alkaline. So which one is acidic and which one is alkaline, and why is one of them acidic and why is it one of them alkaline? After you test with a pH paper, read up on the structure of hair, and you may be surprised by what you find. You notice that there'll be this term which they use called scales. How can there be scales on your hair? Read up more to find out. So I shall not divulge too much of this mystery. Okay, so now let's move on to a reaction which we actually mentioned earlier, neutralisation. So the neutralisation reaction, as we went through earlier, is the reaction between an acid and an alkali to form only salt and water. Only salt and water. So why is it important that I cover this thing here? Because later on, when we talk about the oxides reaction, the amphoteric oxides, the acidic oxides, and the basic oxides, you will need to know what is the ion which actually reacts. And when we move on to the last part of this topic on ionic equations, you will need to know as well what is the ions that are actually involved in the chemical reaction. So quick recap first, just do a quick recap here. Neutralization is acid and alkali giving us salt and water, only. And this is the equation for neutralization. H plus and OH minus gives us H2O. This is the ionic equation. Later on, we will cover a little bit more on how to derive this ionic equation from the original chemical equation here. I have here on screen three classes of oxides. This is actually not something which is brand new. I have already plucked out some of this from the earlier sections. So acidic oxides are mainly the metal oxides. Basic oxides are the non-metal oxides. So the only one which is new here, which we need to introduce before we begin the writing of ionic equations, is amphoteric oxides. So what are amphoteric oxides? Let's understand a little bit more first on the first two oxides, acidic oxides and the basic oxides. So an acidic oxide is an oxide of a non-metal. For example, carbon dioxide. This is a non-metal oxide. The oxide portion is here. This is the non-metal portion. So a non-metal oxide is an acidic oxide. Okay, and if they dissolve in water, they will form acid. So for example, CO2 is a non-metal oxide. So this is an acidic oxide. It can dissolve in water to give us carbonic acid. Sulfur trioxide here dissolves in water to give us sulfuric acid. This is the component of acid rain. SiO2 here, this is a non-metal oxide again, but it is not soluble in water to give us an acid. However, because this is an acidic oxide, based on the chemical reactions it can undergo, it can still take place in a acid-base reaction to give us salt and water. Later on, we will take a closer look at this. Okay, so acidic oxides react with alkalis to give us salt and water. So notice this is similar to the equation we call neutralisation, where acid and base gives us salt and water only. Okay, only. Basic oxides, we covered this quite extensively earlier, are oxides of metals, and those which are soluble are known as alkalis. So common oxides and common alkalis. Similar to acidic oxides, basic oxides can react with acids to give us salt and water only. So recall, this is neutralization, and we have salt and water only. Okay, salt and water only. Which now brings me to amphoteric oxides. So these are metallic oxides which can behave either as an acid or either as a base, depending on what is the other reactant. Okay, depends on what is the other reactant. There are three main amphoteric oxides which you need to know: zinc oxide, lead oxide, aluminum oxide. So let's take a look at the equations here. So why is it amphoteric? So when zinc oxide encounters an acid, okay, when it encounters an acid, it reacts in a neutralization form of reaction to give us the salt and water. So let's say this is HCl, the salt will be ZnCl2. So this is an acid-base reaction. So if this is HCl, zinc oxide behaves as a base. But if I were to switch the H plus out for KOH, I now have a base and a acidic oxide reaction to give me a salt and water. Okay, so depending on what is the other reactant, amphoteric oxides can behave either as an acidic oxide or a basic oxide. Okay, so with acid, this is a basic oxide. With a base, this is a acidic oxide. So these are called amphoteric oxides. So let's quickly attempt checkpoint 6. Some simple chemical equations here. So pause the video now to attempt this checkpoint. Continue the video once you are done. Alright, for checkpoint 6, the first one is a very simple equation: aluminum oxide with dilute hydrochloric acid. So aluminum oxide, if you recall, is an amphoteric oxide. Amphoteric oxide. So this would be a acid, and because this is acid, it will now behave like a basic oxide. And this is the chemical equation. So acid here, and this is the amphoteric oxide, which now behaves like a basic oxide. Next one, for sulfur trioxide with water, so this is an acidic oxide, and because it is soluble in water, it gives us an acid, dilute sulfuric acid. The last equation is for phosphorus 5 oxide with water. Again, phosphorus 5 oxide or P2O5 is soluble in water. So when it dissolves in water, it gives us the acid, and the acid in this case is phosphoric acid or H3PO4. So other than the acidic oxides, basic oxides, and amphoteric oxides, there is still one more class of oxides which is pretty boring, and we call this the neutral oxides. So they are non-metallic oxides that do not exhibit either acidic or basic properties. Hence, they are called neutral oxides. So water is a neutral oxide, carbon monoxide, nitrogen monoxide. Carbon monoxide is a neutral oxide because it is insoluble in water as well. So when it can't dissolve in water, there will be no H plus, no OH minus. It can't behave like an acid, it can't behave like a base. So it is classified as a neutral oxide. Okay, so this is the last part of this topic on writing of ionic equations. We have covered all the equations of all the acids with all the different substances, of the bases with all the different substances, and now it has led us to this area on writing of ionic equations. It is very, very important that before we begin with this section that you know what every single reaction that acids can undergo and every single reactions that base can undergo are. It is very, very important, because without knowing the first chemical equation, okay, without knowing the main chemical equation, there's no way that you can write the ionic equation, because you need to know how to split the main equation first. But once you know that, actually the writing of ionic equations is actually very, very simple. So let me bring you through this in a very stepwise manner. So step one, let's say we are doing the reaction between aqueous sodium hydroxide and dilute hydrochloric acid. So let me blank the screen. NaOH plus HCl gives us NaCl plus H2O. So step one, write the chemical equation. Step 1, write the balanced equation. Okay, step 2. Because this is an ionic equation, we must first split this main equation here into the ion components. So NaOH in aqueous state, NaOH in aqueous state, it means that it can dissociate to give me Na plus AQ plus OH minus AQ, HCl AQ, this is the acid in water, it can dissociate to give me H plus AQ plus Cl minus AQ. NaCl is an ionic compound. An ionic compound, when dissolved in water, can dissociate to give me the ions. So I have Na plus AQ, Cl minus AQ, and I have water here, H2O liquid. So H2O is a molecule. It cannot dissociate to give me H plus or OH minus or anything else. So it remains as H2O liquid. So step 2 is to dissociate into ions. And step 3 is to cancel out the like ions on both sides of the equation. So if we take a look here, what are the like ions we have? Let me change the color of the ink first. We have Na plus and Na plus being the like ions on both sides. So we can cancel these two out. We have Cl minus and Cl minus being the like ions on both sides, so we can cancel this out. And we are left with just these two ions here and water. So for step 4, we rewrite the equation with the ions that are left behind. So what do I have? I have OH minus AQ plus H plus AQ, giving me H2O liquid. And voila, this is the ionic equation. Simple, right? So let's run through this again. Step 1, write the chemical equation. Step 1, write the chemical equation. Step 2, ionize all the aqueous species. Everything which can be dissolved in water can be ionized. So if I have, let's say, if I have NaOH, I can get my Na plus and OH minus. So we need to know what ions, what compounds are soluble in water. Okay, so we ionize them, ionize everything out. Solids, liquids, and gases, we simply write the same compound down. So this is a liquid, we write the same thing down. Step 3, we cancel like ions on both sides. Na plus, cancel, Na plus, cancel, Cl minus, cancel, Cl minus, cancel. And step 4, we copy down whatever is left behind, and we have our ionic equation. Take note, state symbols must always be included because ions cannot exist without a state. Okay, they cannot exist without a state, and they are most stable in aqueous state. So make sure you write the state symbols down. Right. So this is a very simple solubility table which you will need to know. There's more of this. This table is repeated again in the topic of preparation of salts. So from here you notice that all the sodium, potassium, and ammonium based compounds are soluble in water. They are soluble in water. So if I have NaCl soluble, if I have Na2SO4 soluble, if I have Na2CO3 soluble, so long as there's Na plus, it will be soluble. All nitrates are soluble. So if I have NaNO3 soluble, if I have CaNO3, it is also soluble. Chlorides are all soluble except these two, silver chloride and lead 2 chloride. So this is actually a white precipitate. This is also a white precipitate. Sulfates are all soluble except these 3. Carbonates all except this. So if you notice, this is actually the same as this. This is the same. Because so long as you have Na plus, K plus, ammonium present, you will be soluble. And lead 2 compounds all are insoluble except lead 2 nitrate. Because nitrate here, again it is from here. If you have a nitrate present, you will be soluble. Now let's move on to checkpoint 7. Pause the video now to attempt the checkpoint. Continue with the video once you are done. Checkpoint 7 is a very good checkpoint because it allows you to write ionic equations out many times. And the only way to improve in writing ionic equations is to practice and practice and practice. There are 6 questions in checkpoint 7 to allow you to practice on your ionic equations. So checkpoint 7 gives us 6 practice questions. The first one is magnesium with dilute hydrochloric acid. Okay, so step 1, we write the chemical equation out first. So we know it is Mg give me a moment. So we have Mg solid plus HCl equals giving me MgCl2 equals plus H2 gas. So which one can we dissociate? We cannot dissociate Mg, it remains the same. H plus, we have 2H plus, we have Cl minus, 2 Cl minus because the 2 belongs to both of them. We have Mg2 plus here, and we have 2 Cl minus because there's Cl2, there's 2 of the Cl minus, and we have H2. So now we cancel the like ions on both sides. We cancel this, and what is left is just Mg solid plus 2H plus AQ, giving us Mg2 plus AQ plus H2 gas. So this is the ionic equation for part A. Let's go on to part B. So for part B, what do we have here? Part B, we have sodium carbonate in the aqueous state reacting with dilute HCl, aqueous as well. So this is an acid carbonate reaction. It will give us salt plus water plus carbon dioxide. So let's fill in the state symbols now. And we need to balance the equation. There's 2 here, 2 here. So next step, we split the ions out. So we have 2Na plus, we have 1 CO32 minus, we have 2H plus, we have 2 Cl minus, we have 2 Na plus, we have 2 Cl minus, we have water, and we have carbon dioxide. So cancelling for like ions on both sides. Again, what do we have left at the end of the day? We simply have our carbonate ion, aqueous state, plus 2H plus, aqueous state, giving us H2O, liquid state, plus CO2, gaseous state. So the ionic equation over here, you notice that it actually tells us what are the ions, or what are the elements, or which species is actually involved in the chemical reaction. So for the first one, acid metal reaction, the metal is reacting only with the H plus. The Cl minus is not doing anything, and we call Cl minus the spectator ion. Call it the spectator ion. So it is just watching only. That's why spectator. Okay. So for the acid carbonate reaction, only the carbonate and the acid portion H plus is involved in the reaction to give us water and carbon dioxide. The rest of the ions are again spectator ions. Let's move on to the next part. Aqueous calcium hydroxide with dilute sulfuric acid. So we have with us here CaOH2 aqueous with H2SO4 aqueous. So this is a acid hydroxide reaction, acid alkali reaction. This is a soluble hydroxide soluble in water. So this is alkali. So acid alkali reaction gives us salt and water. Salt and water. So if we split now into ions, we have these ions, and next step is to cancel out like ions. We cancel this, we cancel the sulfate. What we have left is simply this equation here. Okay, this very simple equation here, which is 2OH minus AQ plus 2H plus AQ, giving us 2H2O liquid. So we balance it. It's 2, 2, 2. We cancel out. So we have left with OH minus AQ plus H plus AQ, giving us H2O liquid. So this is in fact a neutralization reaction. Okay, so this is in fact a neutralization reaction. This is an acid-base reaction to give us salt and water only. So this is a neutralization reaction. Part D, solid copper 2 oxide and dilute sulfuric acid. So we have solid copper 2 oxide now with dilute sulfuric acid. What do we have? We have a acid and a metal oxide reaction. So you will get us our salt and water as well. Salt and water, make sure equation is balanced. And now let's try to split this into ions. This is the solid, so it remains. This is the acid. This is the salt. And this is water. Do we have any like ions to cancel over each side? Yes, no, we have only our sulfate ions here. And that's it. So if you write this down again, we have CuO, solid, plus 2H plus, aqueous, giving us copper 2 plus aqueous, and water liquid. So this is the ion equation for the acid and metal oxide reaction. Part E, we have aqueous copper 2 sulfate. Aqueous copper 2 sulfate reacting with aqueous sodium hydroxide to give us copper 2 hydroxide, which is insoluble in water. So this is a acid, this is a base, this is a alkali reacting with copper sulfate here. This is not a acid, not a base, but we know that copper 2 hydroxide, which is formed, is not soluble in water. So based on this equation here, what is left? We have Cu out, we have OH minus out. How do we make sure that the left and right side are balanced? We must ensure Na here and SO4 here come together to give us a compound. So we have Na2SO4 aqueous. Alright. So next step, split into ions, Cu2 plus, SO4 2 minus, Na plus, OH minus. CuOH stays by itself because this is a solid, it cannot dissociate. It is insoluble in water. And we have Na plus here, and we have SO4 2 minus here. So we cancel like ions on both sides. SO4 is gone, Na plus is gone. And what do we have left? We have Cu2 plus Aq plus OH minus Aq giving us CuOH2 solid. So this is also known as a precipitation reaction. A precipitation reaction. The precipitate in this case is copper 2 hydroxide, blue in color. The last equation here is a reaction between zinc, which is obviously a metal, so it's solid, with aqueous copper 2 sulfate. So this is a reaction which you will learn later on to be known as a displacement reaction. So zinc can displace copper from copper 2 sulfate because zinc is more reactive than copper. But for this question, it has already given you the products of the reaction. From the solubility table, you know that zinc sulfate is soluble in water. So we have this. Now we split into ions again. And we cancel like ions on both sides. And we get zinc solid plus Cu2 plus aqueous, giving me zinc 2 plus aqueous and copper solid. Alright, so we have practiced 6 ionic equations here. If you need more practice, you can refer to the tutorials. If you need clarifications in any of the earlier sections, please scan through the video again. We have come to the end of acid bases, oxides and ionic equations, so I will see you in the next lecture series. Thank you and have a nice day. Bye bye.